Right now, as you're watching this video, one of Europe's most dangerous volcanoes is slowly falling apart. And we're not talking about some cracks that appear and disappear. An entire side of the mountain is sliding into the sea. And what's most terrifying? Scientists warn this process is accelerating. Sensors placed by scientists all over the volcano's slope are recording something strange. The southeastern side of Etna, a massive rock mass weighing billions of tons, is separating from the rest of the mountain. At first, it was millimeters per year, seemingly nothing serious. But over the past 10 years, the speed has increased dozens of times. Now, individual sections are shifting 1 centimeter every month. And this is no longer just a landslide. This is a volcanic flank collapse. And you know what happens when large volcanoes like Etna fall apart? They don't do it quietly. Imagine this. A huge mass of rock suddenly breaks off and crashes into the sea. Water is displaced with monstrous force. Waves tens of meters high spread across the Mediterranean. Coastal cities will be underwater in minutes. Then the tsunami will reach Greece, Malta, and even North Africa. Millions of people will be at risk. And most chilling, there will be virtually no warning. But why is this even happening? What's making an entire mountain fall apart? Every centimeter of displacement makes the next eruption potentially more powerful and unpredictable. And since all this is moving toward the sea, scientists seriously fear that a large-scale collapse will dump such a volume of rock into the Mediterranean that a tsunami will destroy coastal cities throughout the region. Evidence is mounting with each month. In 2018, a research team from Germany and Italy did something no one had done before. They placed special sensors on the seafloor right at Etna's base at depths exceeding 1 kilometer. The discovery shocked even the researchers themselves. It turned out the entire structure is sliding toward the sea, not only on the surface, but deep at the base as well. This is a clear sign that gravity and magma pressure are working together, destabilizing the mountain. Since then, earthquakes have been occurring along this slope more and more frequently. And these aren't random tremors. These are stress fractures forming as the volcano literally falls apart. Satellite radar detected a deformation pattern corresponding to early stages of a major flank eruption, not from the summit, but straight from the mountain's side. And this is exactly what happened during Etna's most destructive eruption in history. It was back in 1669. Etna's southern slope suddenly shook with a series of deep rumbles. Without any warning, the earth split open, not at the summit as usual, but far below, just a few kilometers above villages. From this crack burst a true ocean of lava, devouring everything in its path. The eruption lasted 4 months. It destroyed more than a dozen settlements and reached the city of Catania, where houses, churches, and roads were buried beneath a glowing sea of molten rock. What's been happening at Mount Etna in recent months makes you wonder, is something similar starting? On June 2nd and 3rd of this year, an event occurred that alarmed all of Sicily. A powerful eruption happened at the southeastern crater, with partial crater collapse. Explosions followed one after another. A column of ash soared several kilometers into the sky. Streams of incandescent lava flowed down the slopes. Videos spread across the internet. The spectacle was simultaneously mesmerizing and terrifying. Authorities immediately raised the aviation alert level and closed areas around the summit to tourists. Catania Airport periodically halted operations due to ashfall. Monitoring assessed the eruption as spectacular but relatively safe for populated areas. Lava remained in the volcano's natural barrier zones. But here's what's interesting. Seismic tremors spread through surrounding towns. Tourists caught on the slopes were evacuated en masse. But Etna didn't calm down. In July and early August, activity became more serial in nature. Numerous explosions in craters, constant lava emissions. Satellites detected powerful thermal anomalies. Video cameras operated around the clock. From mid-August, observers noted a new wave of activity. Explosion intensity grew. Short lava fountains appeared. New cracks formed on slopes. Then something happened that made scientists even more alert. Somewhere between August 20th and 23rd, a new branch of lava flow opened on the southeastern crater flank. Drone operators and geologists recorded flow intensification and expansion of the active lava zone. Authorities again strengthened access restrictions because lava reached lower elevations than usual. Roads experienced rock falls and intense ash emissions. Satellite data showed increased thermal anomaly. This meant eruption intensity was growing. Around September 22nd, another surge occurred. Explosive emissions and intensified activity forced aviation services to raise the alert level. These events were accompanied by pyroclastic material emissions and created nighttime lava fountains visible from the coast. The geochemistry laboratory conducted research on products from a unique eruption that occurred 3,930 years ago. Back then, Etna erupted so-called picritic basaltic magma, an extremely rare and primitive type of magma. This eruption was catastrophic with an explosivity index of 4. For comparison, the recent eruption of an Icelandic volcano with an unpronounceable name in 2010 belongs to this same type. It paralyzed air traffic across all of Europe. Scientists extracted mineral from ancient deposits that contained melt inclusions. These are microscopic fragments of natural magma trapped at depth during crystallization. Essentially, these are time capsules. They preserved information about what was happening in Earth's depths thousands of years ago. These substances were experimentally heated under enormous pressure and temperature, up to 1,330 degrees Celsius. And you know what they discovered? The original magmas contained up to 1% carbon dioxide and 6% water. These are incredibly high concentrations. Where did all this carbon dioxide come from? Previously, scientists believed the source was carbonate sedimentary rocks beneath the volcano, ancient marine deposits that melt and release CO2. But the study showed something completely different. The source is mantle carbon, probably of subduction origin. This means the carbon came from Earth's deepest depths. Further calculations showed such magmas with high carbon dioxide and water content began crystallizing at depths exceeding 30 kilometers, below the Mohorovičić discontinuity, that very boundary separating Earth's crust and mantle. This is direct proof of Etna's magma's mantle origin. But even more astonishing was this magma's ascent time. Scientists conducted mathematical modeling and discovered something remarkable. Maximum ascent time for mantle magmas to reach the surface was 1 to 5 days. Minimum was just 2 to 3 hours. The final ascent stage, the last 15 kilometers, occurred at an average speed of about 1 kilometer per minute. That's 17.5 meters per second. This is actually very fast. Magma literally shoots from the mantle like a cannonball. And the reason for such rapid transport is those very high concentrations of CO2 and H2O. They create enormous pressure that pushes magma upward at monstrous speed. That's why that ancient eruption was so catastrophic. And here's what's truly frightening. Conditions for repeating such an event may be forming right now. Another study revealed yet another surprising detail. It turns out Etna currently releases an exceptionally large amount of CO2. About 10% of all modern global carbon dioxide emissions from volcanoes. That's 9,000 tons per day, 3 times more than Hawaii's Kilauea, which meanwhile erupts 4 times more magma. Where does such a difference come from? The answer emerged when researchers studied rare element ratios in magmas from 4 regional volcanoes. Results showed Etna's magma is characterized by extremely high ratios of niobium to tantalum minerals, higher than any other active volcano of this type. This means beneath southern Italy exist areas of lithospheric mantle extremely enriched with carbon. These areas are located in southern Sicily at depths of approximately 50 to 150 kilometers. And they're moving into the area beneath Etna as a result of tectonic activity, the rollback of the Ionian subducting slab. Simply put, tectonic processes in the region constantly transport new portions of carbon-enriched mantle beneath the volcano. And this may mean Etna's CO2 emissions could become even greater in the future. Besides the volcano sliding into the sea and periodically exploding with lava fountains, it has another strange feature. Its vent constantly migrates. Unlike all other relatively stable volcanoes, Etna's vent literally wanders from one place to another. Since 1971, the southeastern crater was considered the main one. In 2007, the vent shifted southeast. In 2011, it shifted again just a few meters from the old one. But why does this happen? After studying the history of 6 eruptions in 2007, volcanologists finally explained this mystery. They mapped the density of rocks surrounding the vents using satellite observations and geological excavations. It turned out rocks on the mountain's northwestern slope are very unstable. They periodically slide down, causing vent displacement. This process is connected to the fact that Etna's eruption frequency noticeably intensified in the second half of the 20th century. The more eruptions, the more new lava deposits at the summit. The more material at the top, the stronger the pressure on slopes. And here we return to the very problem of gravitational displacement. For a long time, science was dominated by the idea that volcano movement is caused by magma chamber expansion. Magma fills the chamber before eruption. Walls can't withstand the pressure. Eruption occurs. A simple and understandable model, but some volcanoes, including Etna, contradict it. In 2018, a research team placed underwater transponders around Etna's southeastern slope, that very one sliding toward the sea. These devices were equipped with pressure sensors. They recorded the slightest movements of the submarine slope at 1,000 meters below sea level, 12 kilometers from the coastline. Data collected from April 2016 to July 2017 showed something strange. The submarine slope remained stable for a year, but then during one 8-day period, it dropped 4 centimeters, then stabilized. Meanwhile, the magnitude of movement turned out smallest at the summit and greatest at the volcano's base. But if movement were caused by magma inside Etna, the picture would be reversed. Maximum movement would occur near the volcanic center. Moreover, seafloor movement 12 kilometers from shore concentrated along one geological fault. Near shore, it distributed between 2 fault systems. All this indicates movement began in the sea and spread toward the summit. During that 8-day episode, no earthquakes were observed. This indicates movement wasn't caused by seismic activity. It was caused by gravity. The volcano is settling under its own weight. Etna is literally spreading apart under its own weight. And the more eruptions, the stronger this process. Now, let's put the whole picture together. Etna is expanding from the summit in all directions. The entire volcano slides downslope at an average of 14 millimeters per year, but total annual movement toward the sea amounts to several centimeters. This may seem slow, but the stress created inside the volcano is colossal. And here's what truly worries scientists. Catastrophic collapses, where an entire volcano sector descends in a giant landslide, have already happened on slopes of other volcanoes sliding under gravity. Such events occur worldwide about 4 times per century. Destruction from them is monstrous. One Italian volcanologist recently stated, "Etna's southeastern flank is in motion. The question isn't whether it will collapse, but when." The problem is even a small earthquake, deep magma discharge, or heavy rainfall could accelerate this process. A German research team reported slope movement is entirely driven by gravity. This means it's no longer caused only by magma pressure. The volcano is pulled down by its own weight. Sicilian authorities already began revising evacuation rules for populations around Etna's lower slopes. But for now, most residents live their lives unaware that ground beneath them is literally shifting toward the sea bit by bit. This is a slow-motion catastrophe, one that could at any moment cross the line from geological curiosity to full-scale disaster. Eruptions are becoming more frequent. Each adds another level of instability to an already fragile slope. Over the past 50 years, Etna has erupted constantly. Strombolian fountains, lava flows, ash emissions. From August to October this year, activity only intensified. But while the world watches fiery eruptions at the summit, the real threat hides in the depths. The volcano is literally tearing itself apart. And when the slope finally gives way, this won't be just another eruption. This will be an event that forever changes this region. That's all for now. If you found this interesting, subscribe to the channel and give it a like. It will really help us promote this video.